For 80 years, experts insisted no humans reached the Americas before 13,000 years ago. Then, a white band of volcanic ash in Oregon shattered that belief, providing a chemical timestamp that proved humans arrived at least 18,250 years ago, 5 millennia earlier than any accepted theory. Absolute geological evidence, cross-verified in multiple ways, just settled one of humanity's biggest debates. But how did this ash finally close the case? Archaeology in North America has long been shaped by a single idea, that the continent's first people arrived around 13,000 years ago. This belief took hold in the 1930s when distinctive stone spear points, Clovis points, began turning up at hundreds of sites across the United States and Mexico. Over the decades, more than 1,500 Clovis sites have been cataloged, each one reinforcing a timeline that seems set in stone. For generations, textbooks described a migration through an ice-free corridor from Siberia, with Clovis hunters as the pioneers who spread rapidly across the continent. But as excavations expanded, so did the anomalies. In Idaho, at Cooper's Ferry, stone tools surfaced from sediments dated to nearly 16,000 years ago. In Pennsylvania, the Meadowcroft rock shelter revealed artifacts that pushed the story back to at least 16,500 years. These finds, though intriguing, struggled to gain acceptance. Critics pointed to the possibility of contaminated samples, disturbed sediments, or natural processes that might have mimicked human activity. Without an absolute marker in the ground, a line no artifact could cross, each new claim met with skepticism. Relative dating methods, like comparing tool styles or relying on radiocarbon dates from organic material, often produced results open to debate. Radiocarbon can be thrown off by contamination or by the movement of carbon through groundwater. Stone tools, even when found deep in the earth, could have slipped downward through cracks or animal burrows. For every early date, there was a counter-argument, and for every challenge to the Clovis timeline, there was a demand for more definitive proof. By the early 2000s, the list of pre-Clovis candidates had grown, but none could deliver the kind of evidence that would settle the question. Archaeologists needed a way to anchor human presence to a moment in geological time, a natural event that left an indelible mark across the landscape, one that could be measured and verified beyond dispute. The search for that marker became the driving force in the hunt for the true story of America's first people. Volcanic eruptions are among nature's most powerful events, scattering ash across entire landscapes in a matter of hours. When that ash falls, it forms a layer that settles over everything: plants, bones, tools, locking the moment in time. Each layer is unique, carrying a chemical signature determined by the volcano's own chemistry. This signature, made up of precise ratios of elements like silicon, aluminum, and iron, is as distinctive as a barcode. That's the foundation of tephrochronology, a method that lets scientists use volcanic ash as a GO clock. Unlike radiocarbon dating, which measures the decay of organic material, tephrochronology relies on the rapid, widespread deposition of ash. When a volcano erupts, its ash can travel hundreds or even thousands of miles, blanketing regions far from the source. The process happens quickly, sometimes within a single day, so the resulting layer is thin but unmistakable. In the right conditions, especially in rock shelters or low-energy environments, this ash remains undisturbed for thousands of years, preserving a clear line between what came before and what came after. The key is in the chemistry. No two eruptions produce exactly the same blend of elements. By analyzing the microscopic glass shards in an ash layer, researchers can match it to a specific eruption, even if the volcano is hundreds of kilometers away. Laboratories use mass spectrometry and electron microprobe analysis to determine the exact composition, comparing results to reference databases built from known eruptions. If the chemistry matches, the date of the eruption becomes the date of the ash, and everything below that layer must be older. This approach gives archaeologists something they never had before: an absolute timestamp, fixed by geology, not by artifact style or organic decay. At sites where the sequence of layers is undisturbed, tephrochronology draws a sharp line in the sediment, separating the ancient from the merely old. The presence of a volcanic ash layer, identified by its unique chemical fingerprint, creates a boundary that can be measured and verified, closing the door on guesswork and debate. For the first time, researchers could anchor human activity to a precise moment in Earth's history simply by reading the record left behind in the ash. A pale band of ash cuts cleanly across the Rimrock Draw excavation, running like a line of chalk through the earth. Archaeologists first noticed its unusual color and fine texture while exposing the shelter's stratigraphy. The layer stood out against the darker sediments above and below, raising immediate questions about its origin and age. Samples were carefully collected from the ash, each kept free from contamination and labeled by depth. In the laboratory, tephrochronologists began the process of geochemical fingerprinting. Tiny shards of volcanic glass from the ash were mounted and bombarded with an electron beam inside a mass spectrometer. The resulting data showed a distinct chemical profile: silicon dioxide at 72%, aluminum oxide at 13%, and iron oxide at 5%. These ratios are not arbitrary. They act as a chemical barcode, unique to a single eruption in the geological record. The next step was comparison. The laboratory database holds the fingerprints of volcanic eruptions from across the Pacific Northwest. The Rimrock Draw ash matched one entry with striking precision: the Mount St. Helens Set S eruption. This event, dated to 15,600 years ago, left ash deposits scattered over hundreds of miles. The match was confirmed through both major and trace element analysis, with the ratios lining up across every test. With the source and age of the ash established, the layer became a fixed timestamp in the sediment. Everything sealed beneath it, bones, tools, and ancient residues, was now anchored to a moment older than 15,600 years ago. The ash was no longer just a curiosity in the soil. It became the geological marker that would define the timeline for human presence at the site. Tooth enamel from extinct camel and bison, excavated below the Mount St. Helens Set S ash at Rimrock Draw, underwent accelerator mass spectrometry in 2 independent laboratories. Both Thomas Stafford Jr. and John Southan's teams produced results that converged on the same age: 18,250 years before present, with less than 50 years difference between their findings. The enamel's dense structure resisted contamination, and rigorous pretreatment protocols removed any trace of modern carbon. These results left little room for doubt. The volcanic ash, fixed at 15,600 years ago by regional tephrochronology, formed a natural seal. Anything beneath it had to be older. This dual verification, the radiocarbon date from enamel and the geological timestamp from the ash, created a closed system. No artifact or bone could have slipped downward through the dense, undisturbed shelter floor. No groundwater could have carried ancient carbon into these protected layers. The enamel's age was not just plausible, it was locked in by 2 independent measures, each confirming the other. The implications stretched beyond the site. Glacial reconstructions, based on cosmogenic nuclide dating and sediment cores, show that the ice-free corridor between the Laurentide and Cordilleran ice sheets remained closed until at least 13,000 years ago. The evidence from Rimrock Draw, human presence at 18,250 years, precedes any possible inland route by more than 5,000 years. The only viable pathway was along the Pacific coast, where ice never formed a continuous barrier. The story told by the ash and the enamel is not just about a date, but about a migration that rewrote the map of the first Americans. Geological timestamps don't negotiate. They redefine what we know. Today, volcanic ash layers and laboratory precision have set the earliest human footsteps in the Americas at 18,000 years ago. The story of our origins is written in stone and ash, and now the record stands unchallenged. Thanks for watching.